Hello and welcome to a new lecture of classical motion of a single particle. In the last lecture we were discussing different type of conservation principles and how a quantity under different nature of forces, how different type of quantities are conserved, and we have actually also seen that a total of 3 conserved quantities are very important in classical mechanics while discussing the motion of a single particle especially. So, you will see that the first one, if you write the Newton's law for a single particle, it comes out to be m d2r dt2 is equal to f. So, if f is a null vector, then you can easily say that d dt of m dr dt is 0, and it says that m v or m dr dt is a constant of motion, and this is known as the conservation of linear momentum. Then we said that if the force has a specific form where the force can be written as a gradient of a scalar function phi, then is a constant of motion, and this one is known as the total mechanical energy. Finally, we said that if the force acting on the particle is of such a nature that r cross f is 0, that means if the force itself is 0 or even the force is not 0, but this is parallel to r, then this is 0, which we called the torque, then dl dt is equal to 0, and that means that L or r cross m dr dt is a constant of motion. And this constant is known as the this quantity is known as the angular momentum of the particle. Okay. We have also said that a constant of motion, if it is not carrying time explicitly, then it is also known as an integral of motion. Okay. Now, today we will, before doing anything else, we will do two other very interesting cases where you can see that some conservations are actually very usual in nature, and actually the natural forces which we encounter every day, these conservations are inherent in those forces, and that is why we have to learn them. So, we start by a very easy conservation. So, for example, let us say I have the force which is equal to a constant. So, I can say, for example, for a system with, for a particle with fixed mass, the force can be actually proportional to some constant vector g time, and the proportionality constant can actually also be the mass itself. Okay. Since mass is a constant of the system, you can take that as a proportionality constant. Okay. Just for example, if you have that, then you can say the acceleration. So, this is a case where you have a constant force. So, that will be the Newton's law. Now, I am just doing this for 1D and you try to do it in for 3D. Okay. So, in 1D it is equivalent to d2x dt2 is equal to g, for example. And now I am simply saying that this g is a constant. So, of course, this is the 1D motion, for 1D motion I would write, okay. This is a constant. So, I can write now this is as this part as d dt of dx dt is equal to g, and then again I can write this as d dx, okay. So, this is v, so v times dx dt, okay. So, I am simply writing this as I did already in the first lecture or second lecture, dv dt is equal to dv dx dx dt, okay. And that is why finally you will have this thing over here, and g is a constant. Now, dx dt is v. So, I have dv dx times v is equal to g, and if you just integrate, you will actually see your d of v square by 2 will be equal to d of gx. So, now you can actually say that for your system d of m v square by 2, if you just multiply the whole thing over by m, okay. So, you will have minus m g x is equal to 0. If you can actually take g to be minus g just to connect something which we know the form, and then it will be minus and there will be a plus sign. Now, you see that this is something which is a constant for your motion, for the motion of the particle, of course, and so d dt of this thing is also 0. So, this is a constant of motion, and this is the total energy, total mechanical energy, okay. And this one is the potential energy. Since you see why it is possible, this is not a magic, because I said that in 1D, if force can be written as plus or minus some dv dx, where v is an scalar, then our purpose is served, then the force is a conservative force. So, here when this is equal to g, which is a constant, so any constant can also be written as a dv dx of a linear function in x, okay. So, for example, if I can write that, so one possibility is v is equal to gx plus c. That constant you can choose as an arbitrary value, and you can actually set to 0 or some arbitrary constant, that is not a big problem. So, this can be, you can set as v0, and you can say that okay, my v minus v0 is the quantity of interest, and that is equal to gx, okay. So, that is why you see that whenever you are considering a constant force field, at least for 1D, we could show that it corresponds to naturally a conservation, okay. So, this is why this is very important, because this is exactly the case for our gravitation due to the earth, or gravity due to the earth, okay. When earth is pulling every body, so very close to the surface of the earth, where you can actually neglect the acceleration, the variation of acceleration due to gravity, then you can actually think that practically for all the particles, irrespective of its mass, the acceleration is actually constant, and that is why the total energy, which is the addition or the sum of the kinetic energy and the potential energy, is remaining constant during the motion, and potential energy is nothing but this mg times the distance which is covered by a particle which is falling under the earth's gravity, okay. So, you see all these things you already know, but now we are just presenting this from another point of view, that is more like a vectorial point of view, and just we are not here presenting the the point of view that earth is pulling or something. We are trying to introduce the specific point of view where you are thinking that a particle is there, and this particle is experiencing some force due to some agent. That agent can be earth, that agent can be some unknown monster as well, who is also maybe attracting that particle with some force with constant with some force which is constant. Okay. So, whatever be the origin of the force, the system is experiencing a constant force. Okay. Under this, which will be the conserved quantity. That is one thing. Another very interesting feature is that if you just, so I am trying to, I am suggesting you to show this type of problem or this type of conservation, whether you just tell me that whether if your force is a constant force in 3 dimension, okay, then whether you can also derive something like that, a conservation or not. Okay. I am going to another case where the Newton's law is written like this, but this force is of special form. The magnitude of the force is only a function of its distance from some origin which is from where the force is emanated, okay, or the force is originated. So, the magnitude only depends on the distance between the point at which the force is acting and the point from where the force is originated, and this is called r, which is the position vector of that particle on which the force is acting. So, and that r is nothing but the magnitude of its position vector. Okay. If the magnitude of the force is just an explicit function of this distance given by f r, and the force is directed along the line joining O and P, that means the source of the force or the origin of the force and the point at which the force is finally acting. So, either like this or like this. So, that means plus minus r cap direction. R cap direction is the direction which joins O to P. Okay. This is known as the unit vector along the position vector or the radius vector r, okay, where we all know r is nothing but once again x I cap plus y j cap plus z k cap. So, what is r cap vector? This is nothing but x I cap plus y j cap plus z k cap by root x square plus y square plus z square. That means, the whole vector is divided by, so r cap is nothing but actually r vector by r vector modulus. Okay. Yeah. Now, if I have a force like this, what will be the interesting property related to that? First thing is that you can think that if I have a force like this, then what will be r cross f. Achha. So, r cross f, that is the torque. So, that will be r cross f r r cap. So, of course, they are parallel, and that is why it will be equal to 0, a null vector. And so, when your force is of this nature, you know that for your system r cross m dr dt will be, so it gives you, will be a constant of motion. Okay, is known as central force. So, under the central force, the total angular momentum of a particle remains conserved during its motion. Okay. So, that is the first conclusion. The second conclusion is also very interesting. We can take this specific form of this force, which is F r r cap. I can calculate curl of F, and this curl of F, if I calculate, then this will be exactly curl of F r r cap. You know maybe that when you have a curl of a scalar times a vector, then they have a distributive property like this, that you first have phi curl of A plus grad phi cross A. Okay. And then you can easily say that if this is the case, then I can use this over here and I will have f r and curl of r cap plus gradient of f of r cross r cap. Now, this is very interesting. This one you can see this is curl of r cap. So, this is curl of r cap means it is actually I can do with like this curl of r vector by modulus of r. Okay. So, then you can actually modify here the whole thing by introducing a vector term over here, and you can convert that to curl of r vector, or you can do another smart thing right from here that I will suggest more, that right from this step you write the whole thing as curl of f r r cap can be written as some g r times r vector, where your g r is nothing but f r by r. Okay. So, if you write that, then you actually again can write the equivalently that curl of r times g of r plus gradient of g of r cross r. Okay. In last lecture we said and we showed explicitly this is 0. Okay. So, this term will go away, this is 0. Okay. What will be this? If you do this, you will actually show that this thing gradient of g, where g is a function of r, is actually another function h which is a function of r times r cap. That is a small home task I can give you, you can show that easily. And if you actually can do that, or you can actually write some h1 r times r vector. Okay. And so, if it is the case, then gradient of g cross r cap r vector is again equal to 0, because this and this they are parallel to each other and you will have a null vector. So, the result is that the curl of f is equal to 0. So, curl of f is equal to 0 if f is equal to f r r cap. And what is the meaning of that? You all know. This is simply saying that f is a conservative force field. So, f is a conservative force field. So, if I know that f has curl 0 and f has this form, this specific form, can you also calculate the corresponding potential energy or the potential where phi is equal to the potential is equal to minus f dot dr. This is also a small home task to you, okay, to find phi. Okay, that all of you can do, this is very straightforward, okay, in terms of course f. So, you can do that. So, you see that you will again tell me that in nature why we are talking all about, talking all these things about this type of force, because again in nature actually all the fundamental forces are of this nature. For example, if you remember that a particle which is gravitationally attracted by some other particle, then this is actually Newton's law of gravitation. What is that? This is, and if you just think that let us say you have a particle which is of mass m1, and some particle is situated at some distance r with mass m2, then what is the force with which this m2 is attracting m1? This is nothing but minus g m1 m2 by r cube times this r cap, right, where this r cap is exactly in the outside direction, I mean to the outside direction from m2 to m1. That is why minus r cap means it will be towards this m2. Okay. So, that we all know. Now, same thing can be also applied while we are talking about Coulomb's law of electrostatic interaction. So, both the repulsion between like charges and the attraction between opposite charges, they are they are central in nature. Afterwards, there are also nuclear forces, there is Yukawa force, all these things, even like van der Waals force. I mean you can also hear of maybe possibly to model the molecular attraction. We sometimes use the so called Lennard-Jones potential, which is a higher order multiple correction of electromagnetic force fields and also some nuclear force. This is also central in nature. So, most of the cases what we experience, fundamentally all the forces in nature most of the time, unless natural forces, they are central in nature. Okay. Of course, you see like at this particle level, they are central in nature, and the central forces are conservative in nature inherently, and that is why we sometimes say this thing that in microscopic world there is no dissipation, there is always conservation. That is because in the microscopic forces and the fundamental forces are all conservative and conservative in nature, and because they are central in nature, that is why you can show that they are conservative in nature. Okay. So, with this I can stop this part of the lecture. Thank you.